Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. So first of all, welcome to my class. So as you can see, the today's topic is the short circuit ratio of a synchronous machine or the alternators. So this topic is related to the open circuit test and short circuit test of an alternator that we have done for the determination of the regulation. So when we have discussed about the regulation of an alternator, so there we have seen that, so to find out the synchronous reactance we have to perform the open circuit test, we have to perform the short circuit test, we have to perform the DC resistance test to find out the reactance, and then we can find out the voltage regulation of an alternator. So from there we can find out the short circuit ratio. The finding out the short circuit ratio has its own importance in considering that the size cost of a machine, and that's why I am discussing about this topic today. So first of all, we have to understand what is short circuit ratio, or in short it is SCR. Okay, then we have to find out what is the expression for that one, then we have to find out what is the importance of that. So these are the contents for today. So after completion of this class we are able to understand uh, what is short circuit ratio, how we can find out that, and what are the importance of that, what are the mathematical expression of that thing we are able to understand. So let us start today. So first thing, the short circuit ratio is a synchronous machine is defined as the ratio of the field current required to generate rated voltage on an open circuit test, and to the field current required to circulate weighted armature current on short circuit. So we have discussed this previously, that when we have done the different methods of voltage, finding out the voltage regulation, so synchronous impedance method, zero power factor method, so different methods already we have discussed in the previous lecture. So from there we have seen that when we have done the open circuit test, that means the test where a field coil is excited by some rheostat, variable rheostat, so that there is a rated flux generated, field current is flowing, due to that a flux is generated, that flux is cutted by the armature windings, and there is a EMF generation. Now if no load is connected to the terminal, so whatever EMF is generated, that will reach to the terminal. So we, at that time we can say that EMF is E. If we consider the generated EMF is E and the terminal voltage is V, then we can say that at the time of open circuit test of synchronous generator, that time E is equal to V. And when we are considering that the short circuit test, that means when the armature windings are shorted, the terminals of the armature windings are shorted by means of some ammeter, so find out what is the short circuit current is flowing. So in both case, when we are performing this open circuit test, that time we have to set the field current at a rated value, so that the rated terminal voltage may appear. At the same time we can do we have to set the field current at such a value, so that the rated short circuit current can flow through the armature winding when it is short circuited. Now this short circuit ratio is the ratio between that two field current when we need the rated terminal voltage in case of open circuit test, and when we need the rated armature current when we are doing the short circuit test. So the short circuit test can be calculated from the open circuit test characteristics and the rated speed, and the short circuit current characteristics for the three-phase synchronous generator. So as we can see, there is a diagram that is representing the both characteristics. So follow my pointer. So in this axis, this x-axis is representing the field current for both characteristics. Maybe it is open circuit characteristics, maybe it is short circuit characteristics. For open circuit characteristics, we know that this red graph is representing the open circuit characteristics, or it is, as you can see over there, follow my pointer. This is OCC, open circuit characteristics, and this blue straight line is representing the short circuit characteristics. Okay, so now from these characteristics we have already done, though from these characteristics we are now want to find out the what is the SCR. So for that we have to very well understand what is this, and how we have to find out this SCR. So let us start with that one. From the above picture, the short circuit ratio given by the equation shown below. So what is SCR? This SCR is a IF for rated OC voltage and IF for rated SC voltage. So what is OC? Open circuit voltage, and SC is a short circuit current. So now again coming to the this particular figure. So in this figure, so this voltage is the rated voltage and this current is the rated armature current. Okay, so this corresponding to the rated armature voltage, terminal voltage, there is a, follow my pointer very carefully, there is a corresponding field current. So if we apply this amount of field current, that is denoted by OA, this amount of field current if we supply, so then in the open circuit case there will be a terminal voltage appearing, that is equal to the rated voltage of the armature winding when it is acting as a open circuit. And now we have to give this OD amount of this O to D, this amount of field current when we need um, um, rated armature current should flow through the armature winding when it is at the short circuit condition. So we can say that IF for rated OC voltage by the IF for rated SC current, that is given by this OA by this OD, correct? So rated field current for the open circuit test, that is OA, rated field current for short circuit test, that is OD. So that is the ratio that is defining the SCR, the short circuit ratio. Now the point is how we can find out that derivation now we are going to do. Okay, um, since the triangle OAB and ODE is similar, so see there are two triangles are forming OAB. There is a triangle, okay, and there is a triangle ODE. So there are two triangles. This one is triangle. Follow my pointer very carefully. OAB, there is a triangle. This OAB, there is a triangle, and ODE, there is a triangle. That two triangle. Okay, so in that two triangle, as those triangle are similar, so direct axis synchronous reactance, that is XD, is defined as the ratio of the open circuit voltage for a given field current to the armature short circuit current for the same field current. That means what I am going to tell you, for the field current equal to OA, so field current equal to OA, what is the voltage and what is the, so corresponding to this OA field current, what is the voltage and what is the current, that we have to know. So that, see what is written, that for the field current OA, the direct axis synchronous reactance in ohms will be given by, how it will be given by, the at that particular field current what is the voltage by what is the current, what is the open circuit voltage by what is the short circuit current. So what is given written over here, AC by AB. Okay, so what is AC by AB? See, this is AC by this is the AB. AC is representing the voltage, this amount of voltage, follow my pointer, this is the amount of voltage representing over here, and this is AB is the corresponding armature current showing over there for this particular amount of field current. Okay, so this is over there. So per unit value of this XT, this is the direct axis total reactance value is given, that is given by this AC by AB. So now per unit, if we want to find out this is in per unit, so what is the formula? This XD direct axis reactance in per unit is given by XD by base impedance. Now we have to find out what is the base impedance. If we know the base impedance, then you can find out the per unit reactance. So what is base impedance? So what is the formula for base impedance? So base impedance is equal to, as we can see over here, this per phase rated voltage by per phase rated armature current. So the per phase rated voltage by per phase rated armature current. So again coming back to here, So suppose we are considering this waveform is for a particular phase. Okay, maybe phase A, phase B, or phase C. Say if the three phases are A, B, C, then per phase rated voltage means this is the rated voltage that is representing the AC, and in that phase what is the rated armature current? This DE is representing the state rated armature current. Follow my pointer very carefully. Once again I am repeating, that is that AC is representing per phase rated armature voltage, and this DE is representing the per phase uh, armature current when it is at short circuit condition. So let us see, is it as it is written over there. So V rated by IA rated, that is AC by DE. Again coming back to the diagram, AC is this one rated voltage, by DE is the rated current. So if we do that, we can find out the base impedance. So after doing that, if AC by D, if we place that value in this equation, we see in this equation, in this equation. So if we do that, so what is the expression for this XD? That is AC by AB. Okay, and the expression for base impedance is AC by DE. Okay, so if we plot that per impedance reactance, that is given by AC by AB into this DC DE by AC, that is giving us that DE by AB. Okay, so that AC and AC will be cancelled out. So what is the remaining part? DE by AB. So let us check in the waveform what is DE by AB. So this is DE and this is AB. Okay, so these are the two currents. This is DE and this is AB. So DC per unit reactance is given by the two what I can say, two armature currents. Two armature currents are representing over here DE by AB. So now this is the equation number 6, as you can see, and there is the equation number 1. Okay, so where we have the OA by OD. So let us see what is there. Then um, this per unit reactance is given by DE by AB. Okay, and this SCR is given by that AB by DE. This SCR, where follow my pointer very carefully. Okay, so here just pressing that, it is in reverse case. Okay, from the equation 1 and 6 we get SCR is equal to AB by DE, and if we take this AB below of DE, what we get? DE by AB. So 1 by DE by AB. Now what is DE by AB? Follow my pointer, D is AB by XD. So SCR is given by 1 by XD per unit. So this from particular equation it is clear that the short circuit ratio is equal to the reciprocal of the per unit value of the direct axis reactance. So now once again this is the thing, that SCR is the reciprocal of the per unit reactance of the direct axis. Okay, and now this is the mathematical expression. So like this we can find out the mathematical expression. Now the point is, what is the significance? That is the most important part of this particular presentation. What is the significance of this short circuit ratio? Okay, so as you can see, the short circuit ratio is an important factor of the synchronous machine. It affects the operating characteristics, physical size, cost of the machine. Now after this we will I'm going to discuss with you how it is relating to this physical size and cost. The large variation in the terminal voltage with a change in load takes place for the lower value of the short circuit ratio of a synchronous generator. To keep the terminal voltage constant, the field current has to be varied over a very wide range. Okay, now that means when the SCR value is small, the synchronizing power is also small. As the synchronizing power keeps the machine in synchronism, a lower value of SCR has a low stability limit. That means when we are discussing about that um, the SCR value, the SCR value lower means that SCR lower SCR value has the lower synchronizing power. Lower synchronizing power means if there is a little bit change, that means it can lose its synchronism. Okay, so that is not expected from a machine. So so a good SCR value, a higher SCR value is expected, so that the synchronism should be always constant in the machine. So as it is told that in other word, a machine with a lower SCR is uh, less stable when operating in parallel with the other generators. Okay, so that means it is a conclusion, one in conclusion we can make over there, that is a lower value of SCR is not expected, as it is showing us a less stability of the system. But always as a system is concerned, we need higher stability. Okay, so the higher value of SCR is very important for the stability of a system. Now that is written over here: a synchronous machine with the high value of SCR has a better voltage regulation and improved steady state stability limit, but the short circuit current in the armature is high. So when we have a high SCR value, that means the reactance value is, the direct axis reactance value is less, so that means a high current can flow through it. And when we are considering high value current is can flow through it, so the conductor that we have to choose for that particular alternator should be have that capacity. And high current flowing capacity conductor has a high price, and so it has the higher thickness, so the size of the machine will be larger. So that's why it is affecting uh, the size and the cost of a machine by choosing the SCR. Okay, so now let us check what are the effects of that one. The excitation voltage of the synchronous machine is given by the equation. So that is simply the EMF equation: 4.44 kW 5 F turn TPH, where the turn per phase. For the same value of turn per phase, excitation voltage is directly proportional to the field flux per pole. That means if the number of turns is fixed, so then the excitation voltage, that is the generated EMF voltage, it depends upon not generated, the excitation voltage is directly depend upon the flux per pole. So this EF is now directly proportional to the field MMF per pole by the reluctance of the air gap. So if lesser reluctance will give us the higher excitation voltage, and the higher field MMF per pole will give us the higher excitation voltage. So as the synchronous inductance is given by Ls is equal to inverse of the reluctance of the air gap. Obviously that is we know that, but in case of magnetic field, reluctance is acting as the resistive property, as we know in the case of the electrical circuit. So it is inverse of the, definitely it is inverse of the inductance of the same, that synchronous machine. So therefore we can say that this SCR is also inversely proportional to the inductance of the system. So what is the conclusion we can make? So this is the conclusion we can make. The conclusion is, hence the short circuit ratio is directly proportional to the air gap reluctance or air gap length. If the length of the air gap is increased, the SCR can be increased. With the increase in the air gap length, the field MMF is to be increased for the same value of excitation voltage. Hence, to increase the value of field MMF, either field current or the number of field turns has to be increased. All this requires a greater height of the field poles, and as a result, the overall diameter of the machine increases. So that means if we want higher SCR, then we can do the air gap length higher, and if the air gap length is higher, the pole length, magnetic pole length should be higher, and for that the diameter of the overall machine should be increased. Okay, thus a conclusion: for the large value of SCR will increase the size, weight, and the cost of the machine. So at the end I have given some example what is the general range of voltage that we are using for the different kinds of machine. So for cylindrical rotor machine, the value of SCR lies between 0.5 to 0.9. For the in case of saline pole machine, it lies from 1 to 1.5, and that means we can say that in case of saline pole machine, as the SCR value is higher, so it has a higher stability with respect to the cylindrical rotor. For synchronous compensator, the value is 0.4. So these are the different types of SCR we use in our daily life. This is all for today for the presentation. So thank you.